Hello there. In this video, I want to talk about data augmentation is worth 1,000 samples. This paper is published in 16 February 2022. And basically, it talks about how augmentation is important for training a deep neural network. First, they mentioned we propose a method to theoretically analyze the effect of the data augmentation and study questions such as how many augmented samples are needed to correctly estimate the information encoded by the data augmentation? How does the augmentation policy impact the final parameters of the model? They finally show that common data augmentation requires tens of thousands of samples for the loss at hand to be correctly estimated and for the model training to converge. We show that for a training loss to be stable under data augmentation sampling, the model saliency map gradient of the loss with respect to the model's input must align with the smallest eigenvectors of sample variance under the considered data augmentation, hinting at the possible explanation on why models tend to shift their focus from edges to texture. So they mention here that this is the main formulation of the neural network, that we have a target, we have a weight of the network, and we have a transformation, any type of transformation for augmenting the data, and we have our data. We want to train a network with these weights, and this is our loss. So in the appendix, they show that if they want to expand this formulation and separate the augmentation based on the expectation and variance, they will reach to this formulation. Finally, we will get something like this. So we have separated the variance of the augmented data and also the expectation of the augmented data. So by having that, if we back to this formula, they showed that the loss can be defined using equation 11, which is this part is very same to what we had before, but this time this is the expectation of the augmented data, and we have a regularization part, and this regularization part is like a Cholesky of the variance of the augmented data. So they said that we have a variance of the augmented data, and we can decompose it because this is a symmetry matrix. If you use like SVD, we will get U and V same. And if we get the Cholesky or square root of that, we will reach to this formulation. So basically it said it pushes the kernel space of W to align with the largest principal direction of the data manifold tangent space as modeled by the data augmentation. In fact, the largest eigenvectors in Qx represent the principal direction of the data manifold tangent space at X as encoded via variance of the augmented data. So basically, we want to minimize this formulation. For minimizing that, we need to align the weights of the or gradient saliency map of the network or gradient of the loss respecting to the input for the network to be aligned with the smallest eigenvectors of the data augmentation. Because if W is aligned with the largest eigenvectors in the data augmentation, this loss will be increased, these terms would be increased. It's also said, in fact, the largest eigenvectors in Qx represent the principal direction of the data manifold tangent space at X. And if I back the top, it said here, for a training loss to be stable under data augmentation, the model saliency map or gradient of the loss with respect to the model's input must align with the smallest eigenvector of sample variance under considered data augmentation. This is what I showed here. So if you want to reduce this term, we have to have the W aligned with the smallest eigenvectors in the variance. This is one of the important things that they are showing, and also they're showing the variance of the pixel value seen on the left, this one, being much higher for the edges of the cat than for its interior body texture. Means that the parameters during training will be focusing on the cat texture, a phenomenon empirically observed in the deep neural network. So the diagonal of the V, which would be this image, and the pixel covariance between the background pixel and all other pixel For example, 700 rows of the VT, the variance of the augmented data. The focusing of the deep neural network would be on the texture rather than the edges. That's why here we said that if you want to reduce this, we want to put more effort, put more focus on texture. We have to align the weight according to the smaller eigenvectors in the variance of the augmented data. Another important thing that they mention is here, even when considering thousands of samples simultaneously, where each sample's augmentation can complement another sample's augmentation in estimating information provided by a data augmentation, we find that the entire train set must be augmented at least 50 times for a data augmentation policy to be correctly learned by a model. It means that for each image, we need 50 different augmented data. So they have a plot here showing if we increase the training size, and for each training size, if we use different data augmentation, for example, if you have 100 training sample and we have 50 data augmentation samples, we will get a result very likely to be when we use like 300 samples. This is not exactly the same, but for example, if you compare it with when we have only one data augmentation, so we have a significant change if we use enough augmented data. So it means that if we are using a data augmentation, we should use it enough. And enough means like at least 50 times of each samples. They said as training size increases, as the DA samples get redundant with the added samples, closing the performance gap. So when we increase the augmented data, the gap between the data, we have some redundant data because some of the augmented data maybe are correlated with some of the new sample. And that's why it said data augmentation samples get redundant with added samples, which means that we are closing the performance gap. Another part in the paper they mentioned that is here, that they said, we observed that as number of samples grow, as required number of augmentation per sample reduces. Nevertheless, even with thousands of samples, at least 50 augmentation per sample are required to provide an accurate estimate. They showed here that the loss that we calculated based on the augmented data is very similar to a very popular technique called tangent prop regularization. The tangent prop regularization, if you search it in the Google, you will find a paper. They showed that if you use this type of regularization, the model, the machine learning model is invariant, and like shift, rotation, stuff like that. Yeah, so that's it. I hope you enjoyed the video. Have fun.